Hi everyone, I will be teaching how to implement gap statistic. So gap statistic is used for finding the optimal k in k clustering algorithms. The first gap k, which is greater or equal than one standard error below gap of k plus one. So for example, gap of one is still less than gap of two minus standard error. And gap of two is still less than gap of three minus standard error. But gap of three is greater than gap of four minus SE. So gap of three is the optimal k. So we first measure the sum of distances squared between all points and their centroid for some k. And that's called the within clusters sum of squares. We also take the average sum of squares for random uniform data or null reference data. This is the expected value of WCSS of null references. And I refer to WCSS as W. So in total, we subtract from the average of null references distances squared minus the original distances squared. We also take a log to scale the axes by single digits, x and y, and get rid of outliers. So for the code, there will be 7 changes. We'll first make centroids retrievable. We'll make 2 functions, nullrefs and gap.w. Then we'll make a new file for the gap statistic and include functions wref, wgap, and optimal k. I will also post these slides in the description, and I will also have the original document for gap statistic there too. So from the code in the wiki, basically the pseudocode clusters is retrievable, but centroids is not. So what we do is just put centroids outside of the function. That way we initialize it. You have it saved. Pretty easy. So now we move on to our first function, nullrefs. So remember that points is callable outside. It's our original data set. So nullrefs returns a dictionary, and the dictionary will have integer indices for keys and array of points for nullrefs values, key value pairs. And we'll have 0 to num sets, and each set will have the same number of points from the original data set, and each point will be the same length as the original point from the data set. So the point will have values that are randomly uniform. And so typically that would be decimal values from 0 to 1. In this case, it can be integer values. So for example, if you're dealing with RGB values, they range from 0 to 255. So our lower and upper would be 0 to 255. And so therefore each set will be filled with V points, and each sets will contain num set. And then we return sets, which is our dictionary. So gap.w is our second function. And the k-means function returns clusters as an array of arrays, or list of lists. So keep that in mind. So this is our gap function. Remember that centroids is retrievable. We made it retrievable. So we first initialize data points as an empty array. If our argument is null, it's our original data set points. Otherwise, it will be a null reference data set value, key value. So clusters is again an array of arrays. Then we set it to the k-means, our new k-means clusters. Our sum is 0. Then we iterate through clusters, And each element is a list, so we go through the list, clusters I. Then we calculate the sum as the distance from the point and its centroid squared, sum of squares. So remember WCSS, W stands for within cluster sum of squares. So this is the sum of squares. And then we return that total sum, each point and its centroid. So now we move on to our new file for gap statistic. This imports the original file, or refile.ext, refile.ext. ext just stands for extension. It can be anything, same with the name. And we have 4 functions, wref, w, gap, and optimal k. So wref is quite a complex function. It's not too complex, it's just long. So there's 2 parts of it. So we'll go step by step. So we save w and sc outside, and these will be used to calculate our standard error. Then we move into the function, and we set r sets an empty dictionary to be null refs. We set up sum, and then we iterate through the dictionary. And remember, our keys are the integer indices for each array of null reference points. So we're iterating through the indices. So each ref is log of w of each null reference set, null data point. And then we add that to the sum. And then we iterate through the entire dictionary, because we want to calculate the average, which is sum divided by r num, or sum divided by n. And we want to save each of these sum of squares for the null reference data into our W array to calculate standard error. And we'll calculate it soon. So we reset sum to 0, then we iterate through the W array, calculate its sum of squares between the average and summation, and that's sum of squared errors, and observation minus its average. Then we take the square root of the sum divided by n, and that's our standard deviation. Standard error is calculated as standard deviation multiplied by 1 plus 1 divided by r num, or 1 divided by n. B is n in this case. So standard error is usually calculated as standard deviation divided by square root of n. Here it's calculated as standard deviation plus standard deviation divided by square root of n. And I think this just accounts for the small sample size that you'll be using for r num, the number of null reference data sets. So if you make it a large enough r num value, like let's say 100 or 200 even, then standard error will converge to the regular equation, which is of course standard deviation divided by square root of n. I don't think it matters too much. This is how the paper calculates standard error anyway. But back to the topic, we return the average because we're trying to find this, the expected value. We just want to save standard error, pretty much. So the other 2 functions are just one-liners. So you just take the log of the original data set, the gap, the sum of squared differences of the original data set. And then gap is just mirrors this equation here. You take the expected value of the average sum of squared differences of null references, and then you take the sum of squared distances of the original data set. Subtract. So optimal k. Recall that it's the smallest k such that gap of k is greater than or equal to 1 standard error below gap of k plus 1. So this is what the function does. K equals 1. Initial equals gap of k. Go into the loop, initial plus equals gap of k plus 1. And this if statement mirrors this condition. And remember that standard error, we saved that outside here. So we can use it in this function. And then return optimal k, this condition satisfies. Otherwise, k, which equaled 1, now equals 2, and gap of 1 equals gap of 2. And if we keep looping, k equals 2, gap of 3, if gap of 3, if gap of 2 is less than gap of 3, k equals 3, gap of 2 equals gap of 3, k equals 3, gap of 4. If gap of 3 is less than gap of 4, k equals 4, gap of 3 equals gap of 4. So if we don't meet this condition, that means you need to increase the k range. We exit the loop or increase r num. Basically increase the k range, the number of k's in this argument. R num just increases the accuracy. That's all. And return 0 just exits the program. And that's it. So in conclusion, you still must run the original k-means as you did it before. You need to provide the original points array, original data set. And then you can run optimal k inside the new file, just like this. Gap statistic is not the only way to measure the best k for clustering algorithms. There's the elbow method, there's a silhouette method, and there's cross-validation. I found gap statistic to be the most interesting and easiest to use. Implement. And yep, that's it. I hope you enjoyed this video or learned something. Take care.